Hello everyone, welcome to another video on differential equations. So in this video we're going to take a look at one of the more interesting and useful tools for solving differential equations. Specifically, uh, these are homogeneous or non-homogeneous, it doesn't matter, but these are linear differential equations and typically with constant coefficients. But even if they don't have constant coefficients, you'll see that this tool called the Laplace transform is very useful in solving those. There's a lot of ways to introduce Laplace transforms. The way engineers and physicists see the Laplace transform is very different or slightly different from the way mathematicians approach it. So it's a little tricky the first time you're seeing it for a teacher to decide what's the best way to introduce it. But as a mathematician, I'm going to introduce it based on what's best for us, for our class, and what you're expected to do with the Laplace transform, which is using it as a tool to solve a differential equation. Now, the problem with that approach is that you will become very proficient at this. You'll basically learn how to use this tool and you'll become very comfortable applying the Laplace transform, and I can throw at you differential equations and you'll be able to solve them once you master the different ways you can apply this tool. The issue with that is that this is the classical way it's taught, and students often get out of the differential equations course fully understanding how to use this tool, but without having any useful intuition of what the tool is really doing that can help them understand it when they see it in applications, especially in engineering applications. There are really two ways of thinking of this Laplace transform. There's thinking of it as a convenient method for solving differential equations, which is the way we're going to tackle and focus on. But it's also thought of as a useful way to think about and analyze system behavior in what we call the frequency domain or the S domain versus the time domain or the T domain. So bigger than just looking at it from the narrow point of view of a tool that helps you make the process of solving differential equations easier, another way of looking at it is that if it takes a differential equation which represents a system, so let's say this represents some mechanical vibration system like a simple harmonic motion, like an oscillator, you can transform it using this tool called the Laplace transform, and it will take the entire equation and transform it to a different domain that depends on a different letter. So it would transform it from functions of t to functions of s, where s is this like abstract different variable. We usually think of it, again, in applications often as the frequency. And what that does, it gives you a completely different point of view, a vantage point for looking at the same information. So you're still trying to analyze the system, but you're looking at it from a completely different perspective, the perspective of the frequency domain versus the time domain. This is how engineers use the Laplace transform. And what that does, that gives you more insight about what the system is doing. It actually is a much better vantage point to tell you what the system is doing versus the time domain. So in engineers, in the day-to-day operations, when they use Laplace transforms, they often hardly ever do the stuff we're going to do in a math class, which is take the Laplace transform, use the integral form of it, apply it as a technique to solve a differential equation. Engineers typically, and even physicists, use this really to give them, again, that vantage point to predict and analyze the behavior of a system from the point of view or the vantage point of the frequency domain versus the time domain. So please keep that in mind, because the reason I want to mention that is because Mathematicians, unfortunately, are always blamed for teaching it away that then, doesn't make sense to people when they go into the engineering and application field. Well, the reason is exactly what I expected. It's because it depends what you're using it for. So if you're using it as a pure method for solving differential equations, which is what mathematicians use it for, that's what you need to, that's the way you should be taught that topic in a mathematics course. That's what you're expected to know. But of course, if you go into a signal processing or especially like this is used a lot, especially if you're working in control theory. So let's say you're setting up a PID controller and you're trying to uh, analyze the behavior of the system. Engineers spend more time really looking at the system from the S domain by using the Laplace transform, but they hardly find themselves going back to the time domain by trying to solve the differential equation like we do. They find that they just use the Laplace transform to take them to that other realm, the parallel universe, which is the S domain versus the time domain, is just to give them a better view and better understanding of what's going on. So again, I wanted to kind of set the tone up front. That way, when you see this topic, and I know many of you are taking engineering courses or going into engineering, when you see Laplace transform discussed in engineering courses, keep in mind that's going to be different. The other thing that I want to mention, since I'm giving you kind of an overview of things here, a big picture view of things, is that there's another transform. Laplace transform is one example of many special kind of transforms. We call them integral transforms, and I'll explain why we call them that. One other very popular one is called the Fourier transform, which was popularized by Fourier, okay, the French mathematician who was analyzing the behavior of a diffusion equation, a heat diffusion equation, and he invented something called the Fourier transform. He came up with Fourier series, and then it became Fourier transform, which is basically the integral version of the series. And he was able to solve that specific problem he was dealing with. But then people later realized, which this is often the case with things discovered in mathematics, that technique that he used to solve his specific equation that he was worried about is more scalable. It can be applied to many other different kinds of differential equations, and it became a very popular method for cracking open other tough problems. So the Fourier transform and the Laplace transform, it turns out, are actually related. There is a deep connection between the two. Okay. And if I have time at some point, this is again beyond the scope of our course, maybe I will share some other videos or maybe create one of my own that will help you at least get some intuition and know a little bit more about the connection between the Fourier transform and the Laplace transform. They're very similar, right? And maybe I'll share with you again that other point of view, that different intuition of looking at what Laplace transform is and understanding it from that point of view. Because again, many of you are going to go into engineering, maybe signal processing, control theory. You're going to find yourself looking at it from that point of view. Nonetheless, having said all that, what you're going to learn here is still essential. It's still an essential skill to understand one major aspect of the Laplace transform. So somebody who wants to use the Laplace transform, it's very important for them to understand both aspects. How it's used in engineering and how it's used as a mathematical tool to solve differential equations. All right, so let's go ahead and first introduce what the Laplace transform is, right? So definition of a Laplace transform. So I'm not going to write too much stuff here. I'm just going to give you kind of the most important points here. First of all, obviously, this is called Laplace transform. It's named after a person. Last name of that person is Laplace. And as you can see in my split screen here, that's this guy, Pierre Simon Laplace. He's actually a marquis, which is a title. So he was named. People usually refer to him as Pierre Simon Marquis de Laplace, right? So that's, but his last name is Laplace, so we remember him as Laplace. He was born in 1749 and died in 1827, and he has a very interesting history because he has done so many things in mathematics, in physics, in probability theory, in engineering, in astronomy. He even worked for the government. He worked under Napoleon, and he has very interesting eclectic history of the things he's done and he said. He has famous quotes and stuff. And he was also a student of some other great mathematicians like Lagrange and others. And he worked with some great mathematicians like Fourier and others. Uh, I will use this as an occasion to also point out a very good resource if you're curious about mathematical history. There's this website from the University of St. Andrews, and this is a nice place to get reliable resources and important articles and information about the history of mathematics and famous mathematicians and mathematical discoveries. And this right here is the biography of Pierre Simon Laplace. So if you're curious and you want to know a little bit more about what he has done and what he's famous for, and a little bit about his life and upbringing, I would recommend take a look at this page and read. And this would be, I mean, you can obviously find stuff like this in Wikipedia, but this would be, in my point of view, more reliable information than Wikipedia, because this is written by mathematicians who have research history of mathematics and have created this page that's related to the University of St. Andrews. The other thing that I want to mention, this is not necessarily about Laplace transform, but there's another very highly rated website that has, it relates to British magazine on mathematics and sciences called Plus Magazine, and this is their website. And in this website they put a lot of articles and amazing nice little activities and puzzles and information on current events, and they try to present the information to a general audience, so it's not difficult for anybody to read and learn about things in a much easier, more accessible way. They also have, based on what's going on now, of course, with the COVID-19 infections, and they have a whole page of articles that are related to the spread of epidemics and pandemics and how we can model that mathematically. So this is a great resource based on current events to educate yourself further on understanding modeling using differential equations and other ways to model things. Not everything has to be modeled using differential equations, even though we've seen some models using differential equations in this course, because this is obviously a differential equations centric course. But this also gives you some other ways people in real life model real situations, and this is more specific to the spread of COVID-19. So I encourage you to check this out and learn a little bit more about some of these things. And they have a lot of articles that are typically like a page long or 2 pages long, so they're not very difficult to quickly read and get some valuable information from them. And of course they have other resources that they can link you to if you want to find out more. The other thing that I have here is this is just a link to a book. This is the book that Laplace wrote a long time ago. It's a book it's called Théorie analytique des probabilités. That means that's analytical theory of probability. And this book, it was written in French and then translated to Latin. And also I'm sure you can actually research this. If you Google it, I'm sure you can find turn this thing on here. I'm sure you can find an English translation of this, and all of these books are digitized by Google, so you can find them for free. You don't have to pay for these. But the reason I mention this is because if you're curious to see the original or the original text from which this Laplace transform or this method that we call Laplace transform originally was published, this is the text, right? So this is text that was published uh, in, I believe it was 1814, and that was the first time a method akin. So I say akin, which means it's not exactly the same way, but it's a method that's kind of similar to the what we're gonna treat and call the Laplace transform. Laplace's version is actually slightly different from the modern way we use it and apply it. But if you're curious, again, I would seek an English translation of this and then kind of comb through it to see if you're curious about the kind of notation Laplace himself used and how he described this. He used something called generating functions to build up this idea and come up with the idea. But he didn't actually just start from scratch. He actually used a lot of work from Fourier, from Euler, and from other famous mathematicians, and he was able to build on their work, and then he made a very powerful. So just to kind of give you a gist of this, since I'm mentioning the history, might as well kind of tell you a little bit more about it. In the late 1700s, so around 1782 or so, Euler was trying to find ways to solve differential equations by using functions that happen to be integrals of some other functions. So he tried to use integrals to solve differential equations. And he was having some success with that, and he was doing some work in different areas with difficult problems. And Mr. Laplace picked up on that, and he tried to dig deeper into that work and continue and elaborate on that work. And another person by the name of Mellin or Melin or Meyin, some people call him, was able to actually do something similar to that, and it was called the Mellin, MELL transform. He was able to come up with some kind of transform, some kind of way to transform a function using an integral, and he had some success with that. Now the part that none of these guys were able to do that Mr. Laplace was able to do was he didn't actually restrict himself to thinking about integrals that way, just of trying to find integrals that happen to be solutions to differential equations. He actually came up with an integral transform, and he started looking at it as a way to transform an entire differential equation into an equation that's purely algebraic, which means it doesn't have derivatives in it, that you can easily solve, and you can go back and get the solution to the differential equation. That's really what the Laplace transform. And this happened in 1785 when he made that breakthrough, and that's why Laplace gets basically the lion's share of the credit here for doing this. But actually, his version of the Laplace transform that's in this book is very different from the way we're going to use it. The way we're going to use it is closer to what other folks afterwards who took his work and applied it in engineering, like the guy by the name of Oliver Heaviside, and we'll learn a little bit more about Heaviside later when we learn about the unit step function. They were the ones that really made it look more like the modern version that we use. So again, Laplace gets all the credit, or gets most of the credit, but we have to recognize that there was a lot of work here. That was a concerted effort by so many other mathematicians that led to this very important technique. All right, enough said about that. So let me first give you kind of a big picture view of this, because again, this is really the way we look at the Laplace transform. Before we get into the murky details of how to apply it and what does it look like and all the scary stuff, let's actually give you kind of a big picture understanding of how this is going to help us, right? So imagine you have a differential equation, and let's say this is again one of those like simple harmonic motion differential equations, like for example, so you have dE in x of t with initial conditions. Remember what that means. We call that an IVP. Okay. Obviously, the variable doesn't have to be x. Remember when we did this with the engineering applications, like the mechanical vibrations problems, we used x as our variable, x as a function of t. But typically, with most differential equations, we used y of t. So again, you can substitute y for x here. It will be the same idea. All right, so what does the Laplace transform? First of all, we use this letter L, like that, script L, to mean that we're taking the Laplace transform. So what does the Laplace transform do? Well, the Laplace transform is going to be this magical tool, as you'll see, as you'll find out, that's going to turn this differential equation into an algebraic equation The catch, though, that the variables are going to change. So this variable, our main variable here was the t. That was the independent variable. X is the dependent variable. So we were in what we call the t domain or the time domain. In engineering applications, t is going to be time. But from a mathematical point of view, we don't have to focus on that. We just treat it as some letter t. But typically in engineering applications, that's going to be time, right? So what does the Laplace transform do? What's the price it pays for turning an equation that has a bunch of derivatives in it to an equation that doesn't have any derivatives? An algebraic equation basically is just an equation like a regular equation. So here's an example, like 2x plus 3 equals 0. That's an algebraic equation. But if I put x prime minus 5 equals 0, that's a differential equation, right? So that's the difference between an algebra. This is algebraic, this is differential. This one has derivative, this one doesn't, right? So what we're saying is the Laplace transform is going to do this. But the price we pay is that everything now is not expressed in terms of t anymore. It's going to be expressed in terms of a different letter, s. So we get teleported to a different realm or world. We end up in what we call the S domain. Now again, S in applications in engineering and sciences, S typically represents frequency. So typically people like to refer to this in the applied areas as the frequency domain. Okay. So the algebraic equation is going to be an equation in x capital. Now there's a couple things here, conventions I need to get you used to. We use little x, we use lowercase letters when the function is a function of time, but when it gets transformed to a function of s, we use capital letter. So that little x of t becomes capital X of little s. All right. Remember what we're trying to do. We want, at the end of the day, we want to solve this differential equation. So how do we solve this differential equation? Well, we're doing this bypass method. We're doing this avoid the problem, try to solve it by a workaround, and then come back. You'll see what that means when I actually finish this loop here that we're going to show you. All right, so we can solve this for capital X of s because it's algebraic. This will be easier than solving the differential equation. So what's that going to give me? Well, it's going to give me solution capital X of s. So we'll have a formula for X of s. Now remember what X of s means. It means it's some kind of formula that has the letter s in it. There's no t in here at all. We lost that t when we did this transition. It got teleported from the world of the time domain to the world of the frequency domain. But we need to go back. Well, the good news is this transform is invertible. So this process of taking the Laplace transform is invertible. So just like you can teleport from the time domain to the frequency domain, you can teleport back. So we can teleport back via L inverse. So we call it the inverse Laplace transform, and that's the symbol we use for it. All right, so what's that gonna do? Well, that's gonna turn this x of s into a little x of t. So it's gonna change it back to the time domain, and the capital letter becomes a little letter, and the s becomes t. So we get x of t solution to IVP. So we got the solution to this. All right, so I know what you're thinking. Why, right? Why can't we just go through directly from here to here the way we already learned how to do that? Which is perfectly fine, by the way. We already know how to do that. Well, it turns out there are two reasons why we should do this. There are situations where trying to go from here directly is not feasible or is really treacherous. So you run into some kind of obstacle, whether it's a technical obstacle or whether it's a tedium obstacle. You're going to run into an issue of doing this. So let me give you an example. We've seen how to take a Laplace transform, or we've seen how to take a, for example, differential equation, solve it, right? So let's say I had m double x dot plus bx plus kx equals f of t. So if I gave you something like this, that's a forced damped oscillator, you can actually solve it by just finding the xh and the xp, and then you can aggregate the two to get your response. We call that the output, right? F of t is called the input or the driving force, right? The problem though is that this is not always easy to do if you have some, for example, difficult functions to deal with. So let me give you an example of a difficult function. What if the function that you're trying to deal with here, f of t, is not a single formula function? It's a piecewise function. So maybe it's 0 when t is between 0 and 1, and maybe it's sine t when t is bigger than 1. Well, this becomes a little bit tricky to try to solve this problem by using this input. It's not as easy. It becomes a little cumbersome. So this is what I'm saying when I'm saying an obstacle there. So this is some kind of example. I mean, this here is not insurmountable. You can actually do it, but it just makes your life harder, right? It causes you more pain in trying to do it directly. So this process bypasses that. We'll also see that when we have something like this, we can express it using what Oliver Heaviside came up with, which is called the unit step function. And again, that empowers you to use the Laplace transform even more, as you'll see later, and you'll be able to find the solution quicker going around the world like this versus going directly. So that's the issue typically, is that even if you can go directly, it's not always easy. The Laplace transform is going to facilitate things for you. Okay, so that's one of the major reasons why we do this. The other major reason is exactly what I mentioned earlier, which is how engineers and scientists benefit from working with the Laplace transform. It's living in this frequency domain. When you are up here, you can see things about the behavior of the system that you wouldn't see when you are in this zone, in the time domain. So using the Laplace transform is very powerful from two different points of view. It's powerful computationally because it makes your life easier for getting to the formula for the solution if you wanted to do that. But it also helps you qualitatively because it gives you a much better vantage point from which to analyze the behavior of the system, which is really the area that engineers spend most of their time doing and dealing with every day when they're looking at behaviors of systems. They don't find themselves typically spend a lot of time solving for the formula. They spend more time looking at graphs from the frequency domain, and based on these graphs trying to understand what's going on with the solution, right? So both of these reasons are good reasons for us to learn how to do a Laplace transform and how to use it. So hopefully now that gives you kind of a nice overview of what the Laplace transform is all about. Now let's go ahead and dive right in, give you a definition, and get right to it. So here is the Laplace transform. First of all, you've seen the symbol right now. So we take a little f of t function. So notice I don't have to call it x. It could be some function f, could be some function y. The more of the story is that you're taking a function of time, right? And you plug it into this weird integral from 0 to infinity, and f of t gets times by this exponential e to the st dt. Okay, now this is the scary part, right? So let me break this up into pieces that will make it easier for us to understand. First of all, here is our input. This right here went there. Okay, so what did we do to it? Well, we multiplied by this exponential, but notice this exponential here has two letters. Has the letter t, which is obviously our time variable, and that happens to be the same letter we're integrating with respect to. Okay? But it also has this other letter, which is the letter s. Okay, let's think about what happens when you do this integration. Forget the product, how scary it looks. We're not worried about that. We'll deal with that through the examples. But imagine what comes out of this integral, right? So you're taking an integral. Remember, integral is basically like an area. So this is basically trying to take this product of these two functions and is trying to find the area trapped under this graph on the interval of time from 0 to infinity. So let's kind of give you kind of a little visual of that. So let's say my function f of t is a sinusoid, right? So if you took a sine t, so if I took f of t equals sine t and times that by e to the negative st, what's that graph going to look like? Well, forget the s for a second. Let's say s is some number. The sine is a sinusoid, so that's going to be some kind of regular sinusoid like that. But I'm timesing it by an exponential with a negative in it. If s is positive, if you assume s is positive, what's this exponential part going to do? Well, the e to the negative st will be some kind of decaying exponential like that. Now what happens if you multiply those two? What kind of graph do you get? Well, basically you get the sinusoid that wants to do its thing and go up and back down regularly, but then you're multiplying it by the y value of this exponential that's actually crushing it. It's not letting the amplitude stay regular, it's going to make them dampen. So you end up with a graph that kind of looks like this, which again, we've seen this before with damped oscillators, right? So you get a graph that kind of roughly looks like this. So you get, let's see here, I'm gonna try to give you a decent picture of this. So maybe something like this. And you get something like that that keeps dwindling there. And again, it's not a coincidence, it's because of that exponential. So again, you can do the branch of the exponential on the other side, the symmetric of that, and you can see the extent of this. So what is this really doing? Well, this is my t-axis. What this is doing, it's going to measure the area, because that's what integrals do, the area trapped under this crushed up function between the function and the x-axis or the t-axis, and try to measure that total area across the interval from 0 to infinity. So this becomes, here's the area trapped there, here's the area trapped there, here's the area trapped there, add all of these. The parts that are underneath get a negative sign, the parts that are above get a positive sign. So we're measuring the total net area, right? So this is positive, this is negative, positive, negative, and you add on all that up and you're trying to figure out what the answer is. Now, when you do that, your answer is actually going to depend on S. Why does it depend on S? Well, because this right here has S in it, and if you change the value of S, this exponential changes. So this exponential can get steeper or less steep, can change with S. So because of that, if you fix S, if S is equal to 1, for example, you're obviously going to get one answer for the total area. But if S is equal to 1.2, you're going to get a different answer. So the answer you're going to get will end up being a formula that depends on S. And that formula is measuring that total area trapped under this product of these two functions. So the final answer is going to be a function of S. Now, what does it qualitatively represent? That f of S is measuring the total area trapped under that wave. And again, because that total area depends, this picture will change for every different S value they use. Even though you're staying with S values that are positive, then your answer will change. So this is not going to be a constant. This is going to be some kind of formula with respect to S. In fact, we'll see in an example later in this video that if I do sine of t, if I use really sine of t, the final answer here will turn out to be 1 over s squared plus 1. So that's the actual formula that mimics the value of this total area. So if s is 0, for example, this total area will end up being 1. If s is 1, this total area will be 1/2. If s is 2, total area will be 1/5. So the total area depends on what the value of S will turn out to be. Okay, so that's a kind of picture view of things. But here's another way to convince you why the answer should be a function of S. The reason the answer is a function of S is because the integration here is done with respect to t. So imagine integrating this. It doesn't matter how ugly the integral is going to be. You're going to end up with some function of t inside the brackets. So let's call it, I don't know, g of t, right? Let's say that's the entire derivative of all of this. But we also have s here, so that s is going to be treated like a constant. So your function is going to have s also in it. So inside your entire derivative, you're going to have both variables, t and s. But the boundaries relate to t. So when you plug both of these boundaries, and you have to be careful because this is an improper integral, and you've seen in calculus how to handle those via limit, and that's how we're going to handle it. Assuming the limit converges, the t will disappear because you'll plug numbers into the t and it will go away. So when you're done figuring out the answer, you're going to end up with a formula that will have s in it. Okay, so that's again how you end up with an answer that has s in it. All right, so I hope that makes sense so far to everybody, at least qualitatively what this is all about. I'm going to erase all this mess here because that was just to kind of give you a quick synopsis of what this stuff is all about. But the important thing to remember here is that the magic of this Laplace transform is that it's what we call a transform. Mathematicians use different words for different things. So we use the word operator, but we also use the word transform. Like, for example, differentiation is an operator. What does it do? Differentiation is an example of an operator. You give it a function and it takes the derivative of it. But what's interesting about differentiation is that the variable does not change. If I have a function of x and I put it through the differentiation operator, I still get a function of x. And if I put in a function of t, I get a function of t. The variable does not change. That's what separates operators from transforms. A transform is doing more amazing things. Not only is giving you something different, but it's also changing the variable in the process. So you're feeding a function of t, and we use lowercase, that's the convention, so make sure you remember to stick to that. So for functions of t, we always use lower cases. But when you do the transform, you're gonna get a capital letter, that's to indicate that we transformed it, and it's gonna be a function of s, completely different letter. S is still lowercase. So that's the difference between these two. Now, that's in general the idea of a transform. It's doing something like this. Now, like I said earlier, we're only focused on the Laplace transform, but there are several other transforms out there. There's a Fourier transform. There's some other transforms out there that we're not going to focus on. But both Fourier transform and the Laplace transform are a special kind of what we call an integral transform. Why? Because not only they're doing this transformation, but they're doing it using an integration process, right? So these are examples of an integral transform. So that's what the Laplace does. Laplace is a transform, not an operator, it's a transform. Taking the derivative and taking the integral are operators, linear operators, because they still do it, make a change, but they don't change the variable. All right, so that's a very important distinction. All right, speaking of linearity, there's something special about this Laplace transform. The Laplace transform is linear. What does that mean? Well, that means it obeys the rules of linearity. Now, we've seen those with linear transformations. Remember the rules of linearity? Linear transformations, we call them linear transformations because when you applied it to a sum, you got the sum of the answers. When you applied it to a constant times or scalar times a vector, you got scalar times the transformation of the vector. So this is those ideas still apply here, but they apply to this transform. Now, we're not working on vectors, we're working on functions of t. So if you take a Laplace transform of two functions, f of t, little f of t and g of t, the Laplace, you're going to get the same answer as taking the Laplace of each and adding the answers. So this is the way of the Laplace transform to preserve vector addition or function addition, right? If you take the Laplace transform of some constant times f of t, you get the constant times the Laplace of f of t. So Laplace transform is a linear process or linear transform, which is a very powerful tool for us. The other interesting thing about the Laplace transform is this letter S. So what is this letter S? I still haven't told you what S is. Okay. In general, S is complex. So again, especially in engineering applications, when you work with S is going to be a complex number. So S is typically written as some number sigma plus I times some other number omega. Okay. So the Laplace of f of t becomes the integral from 0 to infinity of f of t e to the negative sigma plus I omega times t dt. And you can actually split this. You can write this as integral from 0 to infinity f of t times e to the negative sigma t times e to the negative I omega t dt. Now this is actually, again, some of you may be familiar with Fourier transform, but this is probably going to be an interesting way to introduce it, even if you haven't seen it before. But this actually should jump at you if you are familiar with Fourier transforms, because Fourier transforms are very similar to this. Okay, Fourier transform have this part. Okay. So let me actually write this here in the next page. So I'm going to rewrite it here. So the Laplace transform of f of t is integral from 0 to infinity f of t times e to the negative sigma t times e to the negative I omega t dt. All right, a couple interesting things to mention. First of all, to show you what the Fourier transform is. Fourier transform is very similar to a Laplace transform, but here's what it kind of looks like. So Fourier transform is x of omega is equal to the integral from negative infinity to infinity, and usually there's like a 1 over 2 pi factor up front. Again, some cases people don't use that, sometimes they do. There are different reasons for that, but we don't need to get into it. This is not a lesson on Fourier transform. This is just a quick glimpse to show you the resemblance between the two and the connection between them, because I know some of you will see Fourier transforms in your engineering courses, or maybe you have already seen them. So I want to give you the connection here. That way you understand the link between them and why we need to learn both. So the Fourier transform of some function x of t's, so actually let's call it, I don't know, I'm going to use f for both. Typically we use x, but I'm going to use f just so you can clearly see the comparison. So let me remove this here, make that tiny, like that, capital F of w. All right, so here's what the Fourier transform basically does. It takes the function f of t and it times it by e to the negative I omega t dt. So look at the picture, look at the two, right? So look at the difference between these two. There are two main differences. One of them is minor, that's the boundaries. Typically with Fourier transforms, we allow t to go from negative infinity to infinity because we can go all the way back in time. For Laplace transforms, we usually restrict ourselves from 0 to infinity. There's a reason for that. It's because for most applications with signals, you're going to multiply these by a unit step function. And with the unit step function, you typically start with t equals 0. So multiply so the function before time t equals 0 is turned off, is multiplied by 0. So you assume that your little f of t, the assumption is typically that f of t is 0 for t less than 0. So that's why it makes sense to start from 0 and go to infinity, not go from negative infinity to infinity. But this has not stopped people from using a different version of this, where they can rewrite the Laplace transform in a bilateral way by going from negative infinity to infinity, and it will look like this. Now when you compare the bilateral, then we eliminated that issue with the domain. Now we can see clearly that what shows up here is the same. So what's the part that's different? Well, the part that's different is this part right here. Here we just have f of t. here we have f of t times this exponential. So you can kind of you can kind of think of the Laplace transform is really a Fourier transform, but by taking, instead of a function and plugging it in, you take the function and times it by this exponential before you plug it in. And of course, if you have this 1 over 2 pi up front, you have to remember to divide by that. But essentially, that's the difference between them. So you can think of Fourier transform really is a Laplace transform, but before you do the Laplace transform, you take the function and times it by this exponential signal here. Okay. Now, what do these achieve? Again, that's something for another topic. I will maybe share some other video that's already made. There are some good videos that tell you about the intuition between them over the internet. Again, it's beyond the scope of our course, so that's why I'm not focused on that. But it's good for you to kind of know. Or maybe if I have time, I'll create a video for that that will just focus on the intuition. What basically, and you need to understand both, right? So this connection was key. So if you understand how the Fourier transform works, you'll also understand why we need the Laplace transform. Why do we need this other version where you're basically multiplying by this extra term? So that's again something for a bit too advanced for our class. All right, I digress. Let's forget all that and let's focus on what we are concerned with, which is how to take the Laplace transform. So again, here's the reminder of the important part. So this is 0 to infinity, e to the negative st times f of t dt. And if obviously this converges, then we expect to get a function of s. Now, remember what I said earlier. I said typically s is imaginary. Now here's some good news for us. We don't assume, we're going to work with the assumption that s is real. So we don't work with the imaginary part at all. So that simplifies things for us, because basically you're just going to have, you don't have something like this. So you eliminate the imaginary part of it. So we treat s as already a real number, and that means we won't have to deal with I at all. Right. Now again, in engineering, in engineering courses, you'll find yourself working with the complex, but as you'll see, if you understand and learn it in a math course using the real s, when you go to the engineering class and they show you how to do that with an imaginary, whether it's in a Fourier transform or a Laplace transform, you're not going to have a hard time making the adjustment. You'll see that the adjustment is not bad. Now, if you learn it for the very first time using imaginary and using complex, which includes real and imaginary parts, then it might be a little bit difficult, because that gets in the way of understanding the topic. It complicates the topic for the very first time you see it. So that's why mathematicians like to teach this topic with s being a real number, not complex. But again, keep in mind that broadly, in a broad definition of Laplace, s is treated as a complex number. So it's treated as something of the form some real number plus I times another real number. All right, so that's assumption number one for us, is s is real. So remember that. The other very important thing is obviously the calculus side of this integral. It's an improper integral. So how did we deal with that in calculus? Well, in calculus, you would rewrite this as a limit. So this becomes the limit as b approaches infinity of the integral from 0 to b e to the negative st f of t dt. Now, if you may recall from taking calculus 2, when you did these kind of improper integrals could converge or diverge, because you remember you're trying to add up an area, an infinite area. An infinite area could add up to a finite number or an infinite number. So this limit may exist or not exist. So this limit could converge to a finite number or could diverge. If it converges, that means we get a Laplace transform. We get something that makes sense. We get a formula that tells me what the value of that total area will be for any s. But if it doesn't converge, then the Laplace transform does not exist because we don't get a valid formula for the function of s. So this is equal to f of s provided limit exists. All right, so let's get cracking by trying to find some Laplace transforms of some common functions. Okay, so we're going to make a little inventory, or eventually we're going to build up to a table of by cataloging different common functions we may run into, like a constant function, a polynomial function, a exponential function, a trig function, and what the Laplace transform will look like for each type. Okay, let's start with simple things. What is the Laplace transform of 0? Well, if I follow the rule, I'm just going to put 0 in there. So integral from 0 to infinity e to the negative st times 0 dt. Well, that's just going to be the integral from 0 to infinity of 0 dt. That's like adding a bunch of zeros, right? So you add a bunch of 0 areas indefinitely, you're always going to get 0. So the answer is going to be 0. So there you have it. The Laplace transform of 0 is 0. So the 0 from the time domain gets turned into the 0 of the frequency domain. Okay, how about Laplace of 1? So this becomes the integral from 0 to infinity of e to the negative st times 1 dt. So we got ourselves an integration problem on our hands. So this is a good time for you guys to pause the video and see if you can do the integral. This is good practice and reminder of stuff you learned in calculus 2. See if you can do this integral and see what the answer you get. The answer, as we may expect, should be a formula depending on s, right? So it should be, so the t should completely go out of the equation. All right, welcome back. If you tried it, so let's see. So the first thing you want to definitely do, there's a sloppy way of doing things, and there's a good and correct way of doing things. And the good and correct way of doing things is to make sure that you don't leave out any important details. So especially some of the important things you learn in calculus, like how you write this as a limit. Now, unfortunately, a lot of authors and textbooks, when they present this, to save them writing, to save them space, they do things in a sloppy way. So they just try to find the antiderivative and plug infinity in 0. You can't plug infinity in 0, right? The fundamental theorem of calculus only works when you have finite boundaries. I can't plug infinity. It doesn't work that way. So the proper way you learn this in calculus is to change it to a limit and then do the fundamental theorem of calculus and then evaluate the limit. That's the correct way to do this. So please make sure you do it the correct way, not the sloppy and incorrect way that sometimes even authors do to save them time and space in books. All right, so this right here is limit as b approaches infinity, integral from 0 to b of e to the negative st times dt. Okay, always remember, take care of the integral before you do the limit. So forget the limit. We're going to keep writing that, but we're not going to evaluate it until we're done with this part. Okay, so what do I do with this part? Well, fundamental theorem of calculus. The fundamental theorem of calculus says take the antiderivative and plug the boundaries. But how do I take the antiderivative? An antiderivative with respect to what variable? Now here's the key. Look at what this here. This dt, which means that's my integration variable is t, right? So I'm integrating with respect to t. So how do I handle the s then? Well, you may have seen this, and if you took calculus 3, multivariable calculus, but even if you haven't, basically when you have more than one variable and you integrate them with respect to another, to a specific variable, you treat the other ones like they are constants. So treat the s as if it's a number and take the antiderivative. So if you do that, this becomes limit as b approaches infinity. negative 1 over s times e to the negative st, where t is 0, evaluated between 0 and b. Now notice on purpose I did a couple things here. I had to be specific and tell you where the b and the 0 are going here. That's to make it less ambiguous when I write this, and also to help me when I go to plug things in. I don't want to plug them by mistake into s. I want to plug them into t, right? Now, how did I come up with this part? Well, I used the fact that in general, let's say from calculus, that if I had an integral of ax with respect to x, that's going to be e to the ax, and you have to multiply by 1 over the derivative of ax to compensate for the fact that if I took the derivative of this, a will come out, but I don't have a here. So to get it to work, I have to divide by a up front. And this technically will be plus some kind of constant there, right? So that's what I'm using here. So I'm doing exactly the same thing with two important adjustments. In lieu of x, my variable of integration is t, and instead of a here, it's negative s, all of this. So that's what I'm multiplying by the reciprocal of. So let's get rid of all of this. So this tells me, again, don't do the limit yet. Plug these in first. So put b into the t, and then put 0 into the t and subtract. So this becomes limit as b approaches infinity. And this is going to be negative 1 over s e to the negative s times b minus, this already has a minus, so minus minus becomes a plus, 1 over s e to the 0. Right? Because if you put 0 there, that becomes e to the 0. What's e to the 0? That's just 1. So this is limit as b approaches infinity of 1 over s. Let's write that first, because this is just 1. I'm going to move it up front. Minus 1 over s times e to the negative sb. All right. This is a very delicate step here. So this is the part where it's so easy to make mistakes. So I want you to be very careful and listen carefully to what I'm going to say here. And I want you to critique everything I'm saying. So I'm claiming that this is just going to give you 1 over s, because this right here is going to go to 0 as b goes to infinity. So that's my claim. What do you guys think about that? That statement is a dangerous statement, because dangerous statements are usually statements that are partly true, so it makes it easier for you to want to believe them, but they're not fully true. They're leaving out something very important, and then they can be very misleading. So here I'm trying to be misleading. The answer actually can be equal to 1 over s, but it's not necessarily 1 over s. There's a very important if that we need to include. This would only equal 1 over s provided s is positive. Here's why. Because look what it all hinges on this exponential. So let's look at that on the side here. E to the negative sb. If this number here is positive, then you have e to the negative times some positive number times b, which is going to infinity. So if b is going to infinity times the positive, you get positive infinity. And e to the negative infinity is going to go to 0, because you can write this as 1 over e to the sb. So if the b goes to infinity and this is positive in front of it, e to the infinity gives you infinity, right? Because exponential kind of looks like this. And 1 over infinity will go to 0. But if s is 0 or s is less than 0, that's not going to be the answer. Okay, so it wouldn't even make sense. If s is less than 0, then this right here becomes e to the infinity, which will be infinity. So the answer wouldn't even make sense. This will be infinite plus a constant, so it will be infinite. So you would not get a finite answer. You would get a divergent answer. So that's a big if. That's very important provision to add there, that this only converges if s is greater than 0. So we can officially state that the Laplace transform of 1 is 1 over s, but with a very important stipulation, which is that this is assuming s is greater than 0. So the Laplace transform of 1, we can just remember it from now on that it's 1 over s, but it's important to remember in the back of our mind that there's a domain for that. And the domain for that function of s is s has to be greater than 0. All right. Here's, let's stick again to the definition again. So what I would like for you to try, and so again, this first video is going to focus on this definition, and then we're going to show you some nicer ways of doing things, right? So what I would like for you to do next is try to find the Laplace of e to the at in general, where a could be any number. So again, this is a good time for you guys to pause the video and see if you can figure out the answer for this, and also pay attention to any important provisions about s, and then come back to see how I compute this. All right, so again, I'm going to do the integration. This is called the definition of the Laplace transform. So the integral definition of Laplace transform is 0 to infinity. F of t is this. So it's going to be e to the at times e to the negative st. That's always there when you're doing a Laplace transform. That always gets multiplied by the input function. And now we have to take the integral of this. Now the good news is we can aggregate these two into one single exponential. So we could write this as limit as b approaches infinity, integral from 0 to b, e to the at minus st, which even better, we can write it as limit as b approaches infinity, integral from 0 to infinity, or 0 to b I should say, e to the a minus s times t dt. All right, here we are again. Time to integrate. So what is the antiderivative? Don't forget to keep writing the limit. The antiderivative of this is just going to be the same exponential and multiply up front by the reciprocal of this coefficient here. So that's going to go in the denominator. And this is going to be t equals 0, t equals b. All right, a couple interesting things here, and you'll see why this will be helpful. I'm going to rewrite this slightly differently. So I'm going to write this as negative, let's see, do I want to do it that way? So s is greater than a, so that's going to be, well, I guess we could keep it like this. So let's go ahead and do this. So let's go ahead and evaluate at 0 and b. So we can plug in the b first. So this will be a minus s e to the a minus s times b. Okay, because remember, b replaces t. That's the only place where t shows up. Minus 1 over a minus s times e to the 0. Okay, good news. The e to the 0 is just 1. So this becomes limit as b approaches infinity, 1 over a minus s e to the a minus s b minus 1 over a minus s. Okay, here we are again. Time for that tricky part. So we need to take the limit. So where does b show up? Well, b only shows up here. And I'm allowing it to go to infinity. So I really would like to know what happens to this term. That's what all boils down to. Well, we already investigated this earlier. We said as long as what's in front of it is negative, negative times infinity will be negative infinity. E to the negative infinity will go to 0. So if I want this to go to 0, because I don't want it to go to infinity, because if it goes to infinity, it messes up everything and I get a divergent answer. I want to get a finite answer. So the only finite answer this could go to is 0. And that would only happen if this coefficient here, if this part right here is negative. Because you get negative number times infinity, so negative infinity, e to the negative infinity goes to 0. So this would go to 0, and we would end up with negative 1 over a minus s, which is the same thing as 1 over s minus a, provided s is greater than a. So why? Because if s is bigger than a, then the difference a minus s will be negative. That's the only time it will be negative. So this would only give me a convergent answer. So we would only end up with a Laplace transform of this function if s is greater than a. And if s is greater than a, this is the formula for the capital F of s. So this part right here is the capital F of s that corresponds to this little f of t. So there it is. That's how you do these, right? So that's how you do the Laplace transforms. Now, things get a little bit ugly for other functions. So far, we're already kind of making, showing you a little nice way of how to do this. So let's make a little table. So here we're going to put f of t, and here we're going to put capital F of s, the corresponding Laplace transform. And of course, remember, what gets you from here to there is this script L, which is the Laplace transform. So we already have seen that if this is 0, then you get 0. If it's 1, you get 1 over s, albeit with a provision that s has to be greater than 0. If it's e to the at, then you get 1 over s minus a. So we were building up a nice inventory of corresponding transforms. Well, you could actually prove that there's a few more and I recommend trying this out by using the definition. You can try to figure out the Laplace of sine some number times t. Now, let me write it just to kind of give you a glimpse of the future here if you're going to try out this problem, being e to the negative st sine kt dt. Now, this one is properly ugly, right? It's an improper integral, but it's really horrible. Why is this horrible? Forget the improper integral part for a second. Of course, you're going to write it as limit as b approaches infinity, integral from 0 to b, e to the negative st sine kt dt. I'm talking about this part. This part is going to require integration by parts, and it's one of those weird integration by parts that you may have come across in Calculus 2. It's an integration by parts where you have to do it twice, and when you do it a second time, you get back what you started with. So it's what we call circular integration by parts. So you have to go back around and solve for it. Now again, it's a fun challenge if you haven't seen these before, or even if you've seen them before. But so I leave it up to you as an exercise to do that. And of course, then when you're done with the integration part, which is the tough part, you still want to have you still want to do the limit. So, spoiler alert, I'm going to tell you what the answer is expected to be. If you do the Laplace transform of something of the form sine kt, the outcome is going to be k over s squared plus k squared. If you do the Laplace transform of cosine kt, again, all of these answers were discovered by folks doing the definition over and over and over and over. So this will become s over s squared plus k squared. And I'm going to add a couple more Gonna run out of room here. There's one for hyperbolic sine. There's one for hyperbolic cosine. All right, I'm gonna have to erase this because I need room and I don't want to make this table look horrible. So let's get rid of this part right here. So you've seen that's what you basically have to do to test that these answers are correct. And let's rewrite this. So this is sine kt, where k is a constant. This is cosine kt. There's hyperbolic sine, so you need an h, kt. And there's hyperbolic cosine of kt. Again, k is a constant times t. All right, so what are the corresponding? Now, the good news is that if you remember this one here, the sine and the cosine, it's easy to remember the hyperbolic ones. The hyperbolic, you just make the positive in the denominator negative. So for the sine, it'll be k over s squared minus k squared. And for the cosine, it will be s over s squared minus k squared. So these are the hyperbolic, these are the Laplace transforms of all of these functions. Now, let's add one more. So what if we have a power of t? So basically a polynomial or a monomial. What if we have t to the n? Again, that requires multiple integration by parts, but you can prove by doing the definition that this ends up being n factorial over s to the n plus 1, where n can go from, n is allowed to go from 0 or higher. I mean, you could, if n is 0, basically you get 1, right? So you get this special case here, because you'll get n factorial, 0 factorial, which is 1 by default, and then s to the 1. So you get this one. So that's a special case. So here we'll just put for n greater than or equal to 1, and n is an integer. All right, so the first time you're learning this, you have to do things the painful way, just to get a feel of how they came up with these. So it's a good idea to force yourself to go through the pain of finding the Laplace transform this way. Do it for at least one of the painful ones. Like I would recommend trying it even for not just using any k, just use sine t, so k equals 1, or cosine t. Just do one of those just to kind of help you see the mechanics of it. But after that point, really, you're not going to find yourself having to do this at all. We can just use these as shortcut rules to help us. And we use some of the properties, like the linearity properties. Okay, so that's what we're going to focus on. All right, the other important thing that I want to mention is, when can we take the Laplace transform? So does this work for any function? So basically we need some kind of existence theorem for a Laplace transform. So let me give you an existence theorem for this, and then we'll do some examples that use that table that we just listed. So this table, by the way, we're going to call it, we're going to call these, let's give them a title. Basic Laplace transforms. All right, and I'll actually see here, maybe I should squeeze the existence theorem underneath, and then next page we'll do some examples, because I don't want to take too long with this video anyways. We're reaching kind of the end of it. So let's take a look at the existence theorem. So existence of, or existence of a Laplace transform. Okay, Laplace is the name of person, so we always capitalize the L there. All right, most important thing was that somebody found some sufficient conditions. Now be careful with the word sufficient. Sufficient means they don't have to be true for the Laplace to exist, but if you know that these conditions are true, then you're guaranteed that the Laplace will exist. So somebody basically found a checklist of two things, that if your function passes this checklist, you don't have to worry, you know it's going to have a Laplace transform. But if your function does not pass the checklist, basically the theorem just doesn't tell you anything. It doesn't mean that it doesn't have a Laplace transform, it just means that it doesn't pass the checklist. So what's the checklist? Checklist has two things. Your function has to be what we call piecewise continuous on the interval 0 to infinity. Now that's actually a very good thing because it's not very strict. What do they mean when they say piecewise continuous? Piecewise continuous means it's okay if it has discontinuities, but the discontinuities can only happen at single points, single individual points. So for example, if I have a graph of function that has some kind of discontinuity, so a graph that's kind of broken up like this. That's an example of a piecewise continuous graph, right? Because it only has two discontinuities. But in pieces, it's continuous. It's continuous over this piece, then this piece, then this piece. Maybe the junctions between them are a problem, but we overlook that. So that's really what piecewise continuity means. But of course, it has to be happening over 0 to infinity because that's where you do the integration. We always integrate from 0 to infinity. Okay, now that's the first condition. So f of t is piecewise continuous on 0 to infinity. Okay. The second condition is that f of t is of exponential order alpha. Okay, now this one needs a little bit more clarifying. Okay, if I wanted to give you just a quick description, simplified way of telling you what that means. A function is of exponential order if long term is always going to be smaller than some kind of exponential. So if you can always bound it by an exponential, that's a function of exponential order. As you will be able to see, most functions can be bounded by an exponential. An exponential can be bounded by an exponential. If I have a polynomial, it can be bounded long term by an exponential. So bounded means if I have, oops, try that again. If I have, for example, some graph like this, right? So let's say maybe something does like this. Well, as long as I can find some kind of exponential that's always higher after a certain point. So some point in time after which the graph of this exponential is always above my graph, this function here, f of t, is called of exponential order. So what's this exponential? Well, this exponential could have a formula e to the alpha t. Now, depending on how steep this graph or how high this graph goes, you could adjust the number alpha. So you could make this alpha bigger or smaller to make this exponential steeper or less steep to make sure that it's always above the graph after a certain point. As long as you find some alpha for which this exponential is higher starting from some t value, it doesn't have to start at t equals 0 as long as we can find some t value after which the exponential is always beaten the graph. It's always above it. That's what bounded above means. Then we say that this function is of exponential order alpha because we found an exponential function that has an alpha coefficient that's always higher than that graph after a certain t value, right? So that's really what that means. So if you can find, if your function meets this kind of criterion, and it also does not have any discontinuities beyond individual pieces, individual junctions between pieces, individual dots, breaks, then it's going to have a Laplace transform. All right, so let's write the conclusion, and then we'll give you another mathematical way people like to describe the exponential order thingy. All right, so both of these imply that the Laplace transform of f of t equals capital F of s exists for s greater than alpha. By the way, if you're wondering about the exponential order, here's one way of thinking about it mathematically. If your absolute value of your function f of t is smaller than or equal to some positive number m times e to the alpha t for t bigger than or equal than some capital T, as long as you're able to find this m and the alpha for which this is true, then you prove that it's of exponential order alpha. That's what that means. But I don't want you to get caught up into that much, because we're not going to spend time asking you to prove these at all. This is just for your information to know what conditions can somebody check to know upfront whether the Laplace transform is going to make sense or not. The other important thing to take away from this is that the exponential order matters. So if you know that I can bound it by an exponential order, by a function, an exponential with a coefficient alpha equals 2, then that tells you what s should be bigger than for the Laplace to even make sense. So it even tells you what the formula would be. Now let me give you an example that highlights this. Now remember earlier when we did this, we got this, but we also got a condition with this. What was the condition? The condition was we only could get this answer if s is greater than a. Well, if you actually use this theorem, you'll see why that makes sense. Because the function itself, e to the at, we can say that it's of exponential order a because it's bounded by an exponential that lies right on top of it. Right? So this function is of exponential order alpha equals a. Because from t equals 0 onward, this graph of this function is always, the value of this function is always less than or equal than the value of e to the at, right? Because this allows equality. So and we already know it doesn't even have a discontinuity, so it passes the first check. So by this theorem, we know that the Laplace is going to exist. Of course, to get the formula for the Laplace, we had to use the definition. But we do know it exists for s greater than the alpha. And since our alpha is a, that's why this had to exist only for s greater than a. Right? And again, you can use that with the 1. With the 1, you could use e to the 0. E to the 0t is 1. So you could, so the function y equals 1 is bounded by the exponential e to the 0t. So that's why it ended up existing for s greater than 0. The alpha here is 0. All right. Again, you're hardly going to spend time using this theorem for our purposes. This is just kind of for your information thingy. All right, here comes the part that we definitely need to spend some time on. So what if I give you f of t equals 5t squared minus 3 sine 2t plus 1/2 e to the negative 3t. And I ask you to take the Laplace of this. So what you're going to use is, what you have at your disposal is this table. And these two linearity properties we talked about earlier. Where were they? Right here. Let me box those. So you can use combination of the table and those two rules to help you do this problem. So again, try this by yourself first and then come back when we go over it. All right, hopefully that was successful. So let's go ahead and show you how to do this. So the first thing we do, we have to indicate that we're not, so be careful, you don't write equal to this. These are not equal. Remember, they don't live in the same world. This is f of s, capital F of s, and this is f of t. One lives in the time domain, one lives in the s domain. So one lives in a world that depends on s, and one that lives in a world that depends on t. So they can't be equal. So according to our Laplace transform, we use this L and these curly braces to show that. So when you write like this, that doesn't mean anything. This just means it's the Laplace of something. I'm about to take the Laplace of something. It only makes sense if you put something in between the curly braces. That means you're indicating what the little f of t is, what you're taking the Laplace of. And what should go inside should always be a function of t. Don't forget that. All right. And what comes out should always be a function of s. All right, so Laplace of this, 5t squared minus 3 sine 2t plus 1/2 e to the negative 3t. I can use linearity. Linearity tells me I can write this as Laplace of 5t squared minus Laplace of 3 sine 2t plus Laplace of 1/2 negative 3t. So I basically applied the fact that I can split it over a sum or a difference. Then I use the second property from that, which tells me that I can bring out constant multiples. So I can write it as 5 Laplace of t squared minus 3 Laplace of sine 2t and plus 1/2 Laplace of e to the negative 3t. Now, you could have jumped straight to this. I just showed you basically how I'm using the two rules separately. But once you've seen it once, you don't have to do this over and over. You just go straight from here to there. So basically you spread it across a sum and a difference, and you also pull out any constant multiples at the same time. So now I zero in on these parts. I still have to figure out this part, this part, this part, and of course I still have those constant multiples outside. So this is where those rules from that table are going to come in handy. So for example, we'd know that the Laplace transform of t to the n is n factorial over t or s to the n plus 1. So that means for our problem, this is going to be 5 times 2 factorial over s to the power 3 minus 3 times. We also know from the table that the Laplace of sine of a number k times t is going to be k divided by s squared plus k squared. So for this particular problem, our k is 2. So this will be 2 on top over s squared plus 2 squared plus 1/2 times the Laplace of this exponential. Well, we know from our table, and we proved this from the definition, that Laplace of e to the some number times t is going to be 1 over s minus that number. So this becomes 1 over s minus 3. Well, let's simplify. We don't want to leave this ugly answer like that. So what's 2 factorial? 2 factorial is 2 times 1, so that's just 2. Multiplied by 5, so you get 10. So this is 10 over s cubed. This right here becomes negative 6 over s squared plus 4. And this right here, we can write it as 1 over 2 times s plus 3. We don't have to distribute the 2 into it. Now you could argue, should I make them into one single fraction? So here's my advice on this. If it's gonna take maybe a step to put everything and make your answer simpler and more condensed, then go for it. If it's gonna be way too much work to do that, like it will require 3 or 4 more steps just to get it into a single fraction, then it's not worth it. And you have to make a judgment call based on that. So, but that's the kind of guideline that I use, and that's the guideline that I would give you to use when you're doing these. All right, so that's our answer for that one. All right, I'm gonna stop here, and then in the next video we'll get into much more advanced techniques for doing Laplace, and also we're gonna look at going backwards. So how do you find the inverse Laplace? But for now, this was a good video to at least introduce you to what Laplace is, connections, overall, intuition about the connection between Laplace and Fourier transform. What are some of the broad lines about why we use this, and what the big picture is when it comes to solving differential equations, but we really haven't gotten into any of that. So this is just getting used to the definition, getting used to the table of the basic Laplace transforms, and also just doing some quick examples. But it will get much more fun and much more interesting the more we do this in the next few videos, I promise. All right, thank you for your time, and I hope that you will benefit from this video. See you next time.